Welcome back, friends. This is the second video of the environmental mass spectrometry series. In this video, we will learn the basic principle of mass spec briefly. So let's get started. Today's first question is, what kind of mass does mass spec measure? Mass spec is a method for measuring the mass of an atom in a molecule of substance, so-called analyte. As an example, let's see the mass of a single carbon-12 atom. As mass-to-energy equivalence, we should determine the mass of the atom in its ground state, unbound and at rest. It is about 1.9926 times 10 to the minus 26th power kilograms. This figure is too complicated to handle. So in 1960, IUPAC defined Unified Atomic Mass Unit, U, as 1/12 of the mass of an unbound neutral atom of carbon-12, in its nuclear and electronic ground state and at rest. 1 U is equal to about 1.66 times 10 to the minus 27th kilograms. By using this U, we can handle the mass of carbon as 12 U kilograms. It is very easy to handle. So, in mass spec, a mass of every analyte is given by using the Unified Atomic Mass Unit, U. We should put emphasis on the unit of U as kilograms. The next question is, how do we measure such a small mass? The mass of a single atom, or a single molecule, is too small weight to measure directly. So, indirect measurement by using the Coulomb equation of motion, or the Lorentz equation of motion, is utilized in mass spec. For example, two ions with the same charge, say, two cations or two anions, will repel each other. On the contrary, ions will be attracted to other ions with the opposite charge. This is the Coulomb force. Please be notified that the Coulomb force and the Lorentz force are at work only for electrically charged particles, not at work for neutral molecules. Thus, we must ionize neutral molecules first, to measure mass spec. Controlling the Coulomb force, F, between an ion and an electrode is pretty much easy. If you can measure acceleration, A, of the Coulomb equation of motion, you can measure mass, M, of ion. This is the indirect measurement method for a small weighted ion, by using the Coulomb equation of motion. The next question is, how do we measure acceleration, A, of ion? Actually, we have various types of mass analyzers, and we utilize the equation of motion, depends on the types of the mass analyzer. In this video, only two types of utilizing way are explained, one is for the Coulomb equation of motion, and the other is for Lorentz equation of motion. Let's see the Coulomb equation of motion. In the first step of any mass spec, analyte molecules must be ionized in a proper manner. An obtained analyte ion can accelerate by an electric field. This acceleration depends on the mass of the analyte. Say, the lighter ion will accelerate much, the heavier ion will accelerate less, the lighter ion will move faster to a detector, the heavier ion will move slowly to a detector. By these differences, arrival time of lighter analyte ion is shorter, that of heavier analyte ion is longer. This is a way of mass spec, using the Coulomb equation of motion. For Lorentz equation of motion utilization, analyte molecules must also be ionized in a proper manner. After the ionization, the analyte ion must accelerate by an electric field, and the accelerated ion will deflect by a magnetic field. This deflection depends on the mass of the analyte. Say, lighter ion will deflect much, the heavier ion will deflect less. By the difference of deflection, the ion hitting position on a detector is different. This is a way of mass spec, using the Lorentz equation of motion. We should place the emphasis again on the fact that we must ionize neutral analyte first into positively or negatively charged analyte. By ionizing analytes, the obtained ions can be accelerated, deflected, or moved in a circular motion. Let's discuss the cases where the charge number of analyte ion changed. On the former slide, the charge number of analyte ion was 1. Let's have a look at the same case again. In the case where a mass of the analyte ion is m kilograms, and charge number is 1, the Coulomb force can be described as F equals ZeE. And the inverse acceleration is equal to m over ZeE. But, in the case where the charge number is 2, the Coulomb force can be described as double ZeE. Namely, the ion is pushed forward by the double force, compared with the case where the charge number is 1. And the inverse acceleration is equal to m over double ZeE. Please be notified that small e is the elementary charge, which is a constant, and that you can set electric field, E. So, you can measure m over z, or mass to charge ratio in mass spec. Thus, the basic principle of mass spec is, to generate ions from either inorganic or organic compounds by any suitable method, to separate these ions by their mass-to-charge ratio, m/z, and to detect them qualitatively and quantitatively by their respective m/z in abundance. That is the basic principle of mass spec. By the way, what is m/z in the above Jürgen Gross's definition? I said that you can measure m/z or a mass-to-charge ratio on the former slide. What is the difference? We know m/z appears in a mass spectrum. According to IUPAC's definition, m/z is an abbreviation representing the dimensionless quantity, formed by dividing the ratio of the mass of an ion to the unified atomic mass unit, U, by its charge number, regardless of its sign. The abbreviation is written in italicized lowercase letters with no spaces. Mass spec measures the mass of analyte ion based on mass-to-charge ratio, but values that appeared in the horizontal axis of the mass spectrum are m/z. We should put emphasis on the fact that m/z is not equal to the mass-to-charge ratio. Today's last question is, how do we measure mass spectrum? I mean the instrumentation of mass spec. The upper schematic diagram is Thomson's parabola spectrograph. J.J. Thomson observed protons by using this apparatus in around 1900. This apparatus consists of an ion source, a collimator to narrow a beam of ions, magnetic and electric field generators to analyze ions, and a screen to detect ions. The lower schematic diagram is the instrumentation of a modern mass spectrometer, almost the same as Thomson's parabola spectrograph. A modern mass spectrometer mainly consists of an ionization section, an ion analyzing section, a detection section, and a computer section. Mass spectrometers are grouped into various types according to the ionization and analyzing methods. Major ionization methods and separation methods for environmental mass spec are summarized. In the environmental science and engineering, most samples are gaseous and liquid samples. Gaseous samples are usually ionized by electron ionization, EI. Liquid samples are usually ionized by electrospray ionization, ESI. Volatile analytes in a volatile organic solvent are vaporized by a heater and ionized by EI. Obtained gaseous ions are going to be analyzed by various types of an analyzer, such as quadrupole, Q, ion trap, IT, time of flight, TOF, or Kingdon trap. The commercial name is Orbitrap. Each type of analyzer has its advantage and disadvantage as well. Quadrupole has a big advantage in its production cost, whereas its mass resolution is not so high. Ion trap has a very unique advantage. It is capable of performing multi-stage mass spectrometry, to elucidate the unknown structure. On the other hand, its dynamic range is relatively narrow. Time of flight is good for the high-resolution mass spec of a heavy molecule, whereas its dynamic range is relatively narrow, due to its high-speed detector, MCP. Orbitrap is pretty good for the high-resolution mass spec of a light molecule, whereas its dynamic range is relatively narrow, due to its limitation of small detector chamber space. Orbitrap can work as both a mass analyzer and a detector. This is the summary of this video, the basic principle of mass spec. Mass of every analyte is given by using the unified atomic mass unit, U, kilogram. The mass of a single carbon-12 atom, which is unbound, at rest, and in its ground state is 12, U, kilograms. The basic principle of mass spec is to generate ions, and to separate these ions by their mass-to-charge ratio. The mass-to-charge ratio is not m/z, which is the dimensionless quantity, formed by dividing the ratio of the mass of an ion to U, and by its charge number. Mass spectrometers are grouped into various types according to the ionization and analyzing methods. That's all. Thank you for watching.